Welcome to the third lecture in the lecture series on non-traditional abrasive machining methods, ultrasonic machining, abrasive jet machining and abrasive water jet machining. So, at the end of the second lecture, we had been discussing about the impact of abrasives due to the hammering action of the horn on top of them, and this was the particular figure that we had been discussing. And we had discussed that this was the time axis and this was the force axis, and while this designates the constant static load that we are applying, that means we are pressing the two things, the tool and the workpiece, with a constant static force, but at certain points in time the force is shooting up due to the impacts of the horn contacting the abrasive and driving the abrasive into the workpiece and the tool surfaces. Okay, force is rising and then force is falling off as the horn is receding due to the vibration. So, these are the places where the force blows up, and we had found out a relation in which the force is ultimately found to be this particular maximum force. Okay, these are instantaneous force values with time, and this is the maximum force. By assuming this to be a triangle, we have found out its area, and within one particular cycle we have equated force into time, that is impulse. We have equated the impulses, and from that obtained the relation that F max is equal to 8 into static force into the amplitude divided by the sum of the indentations on the tool and the workpiece surface. Let us now try to derive a relation between the indentation on the tool surface and the indentation on the workpiece surface. How do we calculate them? Okay, so let us have a look. First of all, we will be I think you will agree with me if I say that if you look at this body, if this be the tool and this be the workpiece, at the same point in time, the same force must be occurring between these two and these two. Okay, if we consider, okay, speeds are not very high, so that other forces are not existing, and therefore the same force is creating the indentation on the tool side and the indentation on the workpiece side. Therefore, if that be so, we can quickly say that the projected area pi by 4 into d big D t square, that means on the tool side the indentation diameter. So, the projected area is pi by 4 into dt square multiplied by the flow stress on the tool, since it is undergoing plastic deformation, flow stress for the tool material. This is the expression of the force. Since this force we are considering to be equal to the force on the workpiece side, so it must be equal to flow stress of the workpiece, because the workpiece is also undergoing plastic deformation, multiplied by the projected area, this time dw square. So, if we have established that, it essentially means that these two will be equal, pi by 4 will cancel out from both sides, and therefore dt can be replaced by, once again, that relation, Pythagorean relation that we had derived. So, from that, by replacing big dt, we are getting delta t into d1 and delta w into d1. d1 cancels, this 4 cancels out, and we ultimately have a relation that delta t by delta w is equal to sigma t by sigma w by sigma t, and that is equal to hardness of workpiece by hardness of tool. That means we are saying when a body is plastically deforming, the flow stress can also be considered to be an expression of hardness. So we will use them interchangeably in this particular analysis. So if we have delta W common here, if it is taken common, we will have 1 plus delta T by delta W, and therefore we can replace it by delta sigma W by sigma T. So let's see that. So we have taken delta W common, and therefore delta T by delta W we are replacing by sigma W by sigma T as per previous calculation, and after that we are replacing this particular expression sigma W by sigma T or HW by HT by lambda. So lambda is equal to sigma W by sigma T, as is obvious. Okay, it's just a simplification of terms so that it becomes easier to handle. However, you might still ask, what have we, by the way, delta W has been replaced by delta. We have dropped that subscript W, because once that subscript T is gone, it is not necessary for us to continue with W. Okay, we can well drop it, and therefore we have dropped it. But we should still remember that it pertains to the deformation on the workpiece. So you might ask me that what is all this leading us to? We still don't have an expression of F max. Do we? Do I know delta? That means the indentation on the workpiece? No. At least I cannot find it out analytically. So let us proceed with the analysis. We try to analyze it from another angle. What we say is the F max force must be the total force which is coming due to a number of abrasive particles. Therefore, we say that it must be equal to total number of abrasive particles which are active under the tool surface. Let us call it N. N number of abrasives offer this small force, and therefore it is added up altogether to create F max. What is this force? This force is simply sigma W or HW, whichever you would prefer to use here, sigma W multiplied by the projected area. So there is nothing wrong here. This is the small amount of force per abrasive, and this is the total number of abrasives. So therefore we are multiplying N to get the total force coming from these individual abrasives. Now N has to be estimated. What is the value of N? How many abrasives are actively participating in the material removal at one point in time? For that we make use of the expression of concentration. Concentration is volume by volume fraction of abrasives inside the abrasive water slurry. What does this mean? Whenever you are working on the ultrasonic machine, we will make some gross or broad based estimations. You might ask your student that how much abrasives are you using in this experiment? He will say, why is that important? He will say, because I have to make an estimate of the concentration of abrasives, because it's very much an expression used in the analysis. So he will say that actually there was 1 bucket of water, and to that I added say half a bucket of abrasives. So you will say, fine, then that is the estimation. That means in 3 parts of slurry there is only 1 part of abrasive, so that the concentration comes out to be 1/3. And therefore we make an estimate now of the concentration from volume considerations. So if the cross section of the tool be A, the tool surface has a cross section of A, big A, small a is the amplitude. Therefore we can say concentration must be equal to the total volume under the tool multiplied by the concentration. This is the total volume of abrasive divided by the volume of each and every abrasive, and you will get the number of abrasives. So, concentration multiplied by area of tool multiplied by 1 abrasive grit diameter. That means we are assuming that there is a mono layer, that means a single layer of abrasives possible under the tool surface. So, if that be so, the total volume under the tool, which is housing or accommodating the abrasives, is A into D, multiplied by abrasive concentration is C. C into A into D must be giving you the volume of abrasives present under the tool. That's good. Now, if we divide it by the volume of abrasives, I mean volume of an individual abrasive, we will get the number of abrasives. So, we divide it by 4 by 3 pi r cube. We are not using r, but we are using d, and therefore, it comes out to be pi by 6 into d cube. Pi by 6 into d cube. So, that is written at the bottom. So, CAD divided by pi by 6 d cube. That gives us the expression of number of abrasives participating in the machining process at a particular point in time. So, we make some simplifications in that, because you will see that there is d at the top, d cube at the bottom, and therefore, you will have d square at the bottom. So, you will find here we have d at the top, d cube at the bottom, so that we have d square at the bottom. We have large d square here, and therefore, we are having it here once again. Sigma w is occurring here, and all the other terms are, 3 comes here, C comes here, E comes here, and what is this 4 into d d1 into delta? Oh, that is coming from d square. D square is simplified and put here, and 2d square was already existing, and therefore, we can still remove the expression of d1. d1 we are replacing by mu into d square. Mu into d square. Please remember, d1 is the lobe diameter, and d is the grit diameter, and they are related as d1 equal to mu d square, and therefore, we have replaced that. So, all these variables are crunched. Whatever can be cancelled out, it is cancelled. D square cleanly cancels out with the d square at the bottom, and therefore, we have C coming here, E coming here, delta coming here, mu coming here, sigma w coming here, and 6. We are not very much bothered about these constants, because ultimately you will see that we will be dropping them and expressing the relation as a proportionality relation. So, anyway, so this is F max. Remember, F max we have now found out from the considerations of concentration, and we had already found out the expression of F max here, and therefore, we equate the two. When we equate the two, we get an expression of delta square. Why? Because delta was occurring here, and delta has occurred already there, and therefore, by cross multiplication we can say delta square is equal to this. Let us inspect what we have here. We have delta square, that means deformation or indentation square, is equal to 8 into F, that means static force, into amplitude divided by 6 into concentration square cross section of tool, mu sigma w 1 plus lambda. That is good. We have now got an expression of delta. You might say, if I give you the machining conditions, can you find out delta for me? Yes. F is known, say F is 10 newtons, E is the magnitude given to be, say, how much, say 40 microns, and say C is given, concentration is 0.2, E is given to be a particular cross sectional value, okay, and mu is given, say 1, sigma w is provided for a particular material, lambda is also provided. Lambda is hardness of, if you remember, hardness of workpiece by hardness of tool. So delta square can now be estimated. Once delta square can be estimated, we can easily find out the material removed, because material removed we have already assumed to be hemispherical chunks with delta indentation and large d as their edge diameter. So material removal rate, we say, first of all, coming from every impact, it is equal to, instead of 4 by 3 pi d cube by 8, it is 2 by 3 pi d cube by 8. That's good. Into the number of abrasives which are taking part, into the frequency, because so many times per second this material is getting removed, and therefore by simplification we get f into 1 by 12 into pi into d cube, and n we have already computed it to be, if you remember, c into a into d divided by pi by 6 into d cube. This I am just importing from the previous derivation, and therefore after that we start crunching the numbers. That means that we replace them by known values, and then we ultimately simplify and find out what we get. For example, d cube can be replaced by 8 into delta to the power 3 by 2, okay, delta to the power 3 by 2 into mu to the power 3 by 2 into d cube. You might say, where did you get that from? Well, if you remember, d is equal to twice root over of delta into d, okay, delta into d1. So if d cube is taken, we will have delta to the power 3 by 2 and d1 to the power 3 by 2, and from d1 we bring in d, and therefore it becomes d cube, and from the concentration we have c into a, etc., etc. I am not working term by term now, because I am sure once you have got the hang of it, it's very simple calculation where you have to stay alert, not make any careless mistake, and definitely you will arrive at the correct answer. So after that, this becomes equal to, now let us start collecting the coefficients, and you will find that c to the power 0.25 is going to occur. How so? Let's quickly track back. We have from the n term, one c occurring, so that's one full c. And what is the other source of c? The other source of c is coming from the expression of delta. Remember, we had found out an expression of delta square. Now we are replacing it in this particular expression, and we have got c to the power 3/4 in the denominator. So c at the top and c to the power 3/4 at the bottom gives us c to the power 0.25 or c to the power 1/4 at the denominator, at the numerator. So in the same way, I am now not going to go into each and every term, but we will get c to the power 0.25, area to the power 0.25, static force to the power 0.75, amplitude to the power 0.75, mu to the power 0.75, diameter of the grid, frequency of vibration divided by the flow stress or the hardness of the workpiece material, lambda, 1 plus lambda to the power 0.75 in the denominator. Okay. So this is the expression of MRR, or rather MRR is proportional to this particular expression. So ultimately we can say we have got a good estimation of the terms to which MRR is going to be proportional, and we will be able to utilize this expression to good effect in order to derive material removal rates. Okay. So now let's go on to the next one. So we have derived an expression for material removal rate. Let's try out some MCQs before proceeding on to harder problems. Let's see. For making a circular section hole, So I'm basically making a hole which has a circular cross section of diameter 5 millimeters in mild steel plate. Mild steel means that the carbon percentage is around 0.2% perhaps. Mild steel plate of thickness 10 millimeters. The most appropriate process would be die sinking EDM, none of the others, drilling with continuous wave laser, ultrasonic drilling with abrasives, ultrasonic drilling without abrasives, conventional drilling, and drilling with pulsed laser. First of all, die sinking EDM. Should we use that? Well, it can be used. There's no harm in using it, but we have to first find out whether there's any other competing process which proves to be more convenient. None of the others means that you think that none of them will be applicable. No, this is obviously not correct. Drilling with continuous wave laser. What's continuous wave? Continuous wave means that it's not pulsed, but the level of power of the laser, output power level of the laser, remains constant with time. Do we use that? Well, let's see. Let's go ahead with the other options. Ultrasonic drilling with abrasives. Yes, this can definitely be used, definitely. But let's see. But mind you, as this is mild steel, it will be a ductile material, and you won't be getting very high material removal rate with mild steel if you use ultrasonic drilling. Ultrasonic drilling without abrasives, well, then you will be out with, you will be without abrasives, and therefore your material removal rate will not be high, provided it will cut at all. It's not specified how this drilling is being done, but without abrasives, you'll be at a disadvantage. Whether it's some other kind of material removal method is being employed or not, it's not clear. It might be that you won't be able to cut at all if you're using conventional ultrasonic drill without abrasive. Now comes conventional drilling. That means using a conventional drill tool and trying to machine the material. Last of all, drilling with pulsed laser. Just like you have continuous wave laser, you can have pulsed laser also. Now, what is this pulsed laser? Now, in case of a pulsed laser, it allows vapor and projectile material droplets, metal droplets which are melted, to come out of the hole during the times during which the laser is off. If the laser is continuously on, material will continuously get produced, and it will be difficult to remove it from the blind hole. So, pulsed laser is better than continuous wave laser for drilling, but whether it's appropriate here or not, that we have to now find out. The answer to this is conventional drilling. And why so? Because conventional drilling is very inexpensive compared to these processes, and it gives you good geometrical accuracy and surface finish. So why go for the other methods which might be costing you more, which might not be giving you well defined geometry, which might not be giving you good surface finish? Why go for them if you have conventional means applicable? Use the conventional means here, and that is the answer. Glass can be machined by EDM and not by USM or ECM. Glass can be machined by ECM but not by USM, EDM, none of the others. USM but not by ECM or EDM. So, glass being a non-conductive material, it cannot be machined by EDM or ECM, and therefore the last option is correct, which says that glass can be machined by USM and not by ECM or EDM. The horn in the USM process is a tool that is commonly tapered towards the machining end so that micromachining tools can be held, higher pressure can be applied on the work surface for the same static load, none of the others, and weight of the machine is less and hence vibration would not be damped out. So first of all, if you want to hold micromachining tools, the tools themselves can be small. Why does the horn have to be small in that case? So the first option is not correct. Higher pressures can be applied for the same static load. Once again, the horn can well have a large diameter all through, but the tool it is holding at the end, that only can be less in diameter, and that should take care of what is being claimed. So the diameter does not necessarily, have to be less for these cases. Weight of the machine is less and vibration would not be damped out. This is also not, not the reason for which it is commonly tapered. It is commonly tapered for a completely different reason. That is amplification of the amplitude. The amplitude is magnified at the tool end of the horn due to its tapered shape. Tool in USM may be made of aluminum oxide, glass, steel, ceramic. Tool here means that at the end of the horn there is something put or attached which is having the shape, conjugate shape of the final shape that you want, and it should not take up much damage from USM. If it is glass or ceramic, definitely it will take up damage. If it is aluminum oxide, then also it will take up damage because aluminum oxide is reasonably brittle. So steel must be the answer. It has to be made of steel so that it itself will not take up much damage, being basically a ductile material. Okay. And it will not crack up. Acha. Let's have I don't think we have time enough to discuss this problem, but you can treat it as a take-home problem. Let's see quickly what it says. Ultrasonic machining. Mind you, here I think I should mention that in the final exam and in the assignments we will only have multiple choice questions, so that all these these elaborate problems that we are going to discuss in the lectures, ultimately they will come in the form of multiple choice questions, but we will discuss the process in the lectures. So ultrasonic machining is carried out on a work material A and work material B. The tool is made of a work material C. The material removal rate for machining material A with tool material C is MAC, and that for machining material B with tool material C is MBC. If the hardness values of A, B and C are 7,000, 5,000 and 1,000 in newtons per millimeter square respectively, find the ratio of MAC by MBC. Given material removal rate in case of ultrasonic machining is given by this expression, which we have already derived. So we have no issues with that expression where all these things are derived. Let's have a quick look at these. F is the static force, A is the area of cross section, abrasive grid diameter is DG. Okay, so they are using DG instead of D. That's all right. Amplitude of vibration is A0. So they are using A0 for amplitude of vibration. Workpiece material fracture strength equal to its hardness equal to sigma W. Tool material fracture strength, it's better to use flow strength in this case. Flow strength equal to its hardness equal to sigma T. C is equal to abrasive slurry concentration, and lambda is defined as sigma W by sigma T, and take hardness equal to fracture, it should be flow strength. Okay. So, we will discuss the answer to this one in our next lecture. Thank you very much.